Good evening, everyone, and welcome back to session 6 of regulatory analytics. So, our focus today would be linear regression. Now, as the name suggests, we are talking about a linear model. A linear model means a line based model. We are trying to build a model that will do the line based regression. Now, we have two different kinds of algorithms. As we have seen, we have classification and prediction. So what is the difference between the two? In classification, we are trying to classify the object based on some features. All right. But in regression, we are trying to predict some output. Now, this means that the output is continuous here, especially in linear regression. If the output is not continuous, then we use something called a logistic regression. All right. So here we have a linear regression. Here we are trying to satisfy the line equation. The line equation, simple, y equals to m of x plus b, where m is the slope or the intercept of the line and b is some constant assigned to this line. So how does it work? So we try to build a model where this equation will be satisfied to the best of its ability. Okay, so that is our aim here. So what are we going to build? So let's move forward here. So it is going to search for a linear relationship between the various variables. You will have a lot of columns. In columns, we would have two different values. We would have the x value and the y value. The x is our independent features and y is our dependent features. So using these features, we are trying to build an algorithm that is going to predict our future. Using the independent variables, we are trying to look at their relation to the output. Okay, whatever the output may be, we are trying to look at its relation. Okay, so what we'll do here is we'll take some independent features and we'll try to build a model to predict this value. Okay, we are trying to predict this value. Now here, the important point to remember is that our y is going to be continuous. X can be anything. It can be continuous. It can be discrete. Or it can be a combination of these two. So it can be any of these values. Okay. So we have to, if you're building a linear regression model, y has to be continuous. Otherwise, it will not be a linear regression model. All right. So here we use something we call as ordinary least square methods. Excuse me, just 1 second. Sorry about that. A really bad cough. So we are trying to build a regression model using something we call as the ordinary least square method. Now, using this OLS method, we are trying to predict the accuracy of our algorithm. Okay, so we have this line. This is our y equals to mf m of x plus b. Now, one thing we have to remember here is that when we are talking about linear regression in terms of data science, we don't use terminologies like m or b. Here the equation is written as y equals to beta naught plus beta 1 of x. Here beta naught is your some constant value and beta 1 is the coefficient of x. Okay, so here we can see that this beta naught value is a non-zero value. So here we have built a linear regression model using this line that has been given some constant value as well as some coefficient value. So the responses fall on this line. The predicted values fall on this line. So here we are trying to take the difference between the actual values and the predicted values. Predicted and actual. We are taking the difference and we are coming up with the error. This line is known as our residual line. This is depicting how far away from the actual value is our predicted value. So this sort of acts as a error calculation matrix. Okay. So here we are trying to minimize this values. All right. So we are trying to minimize this residual. But here in linear regression, we also try to calculate something known as our R square value. R square value is the value which is going to represent how much of the variation in output is explained by input variables. So basically we are trying to figure out how much of the variation, how much of the variance of the output is captured by our input variables. Now, if we remember, we have covered things like this before in the session, not in this one, but in the data science session, we have talked about PCA. In PCA, we are trying to capture the variation of the column. However much variance we are able to capture within the few columns, the better it is. So the same thing we are doing here. So this R square value is always between 0 to 1. Okay. So here the idea is the closer it is to 1, the better it is. So if your R square value is between, let's say, 0.65 to 0.8, this is moderate R square value. This means that this value is good, not the best. If your R square value is greater than 0.8, this is strong value. This is what we are trying to do. We are trying to make sure that our R square value is going to be as high as possible. Okay. So let's see how it is calculated. Here we are taking the sum square of residuals. That is our y value, the predicted value minus the mean value of y. We are taking the square of it. Then we are taking the sum square of error, where we are taking the y minus the predicted y value square. And then we are taking the total sum of squares, which is this residual squares plus the error square. Okay, so this is how we try to find our R square value. R square value is given as sum square of residual divided by total sum of squares. Okay, and this value always has to be between 0 and 1. If for some reason your value is exceeding 0 or 1, that means you have made a mistake that can be quite complex to overcome. So this is in regards to linear regression. Okay, and if we talk about multilinear regression, in that also we are building the line equation. It would look just something like this. So on up until the last value. So here these values are not as important. The important bit is the coefficient. Okay, these coefficients are giving some sort of weightage to all values, input values. So we have to make sure that we are assigning the correct coefficient value to the correct variable. All right. So we use NumPy, we use scikit-learn. So what we'll do is we'll go to our data and we'll try to look at how we perform our linear regression problems. So first, let's talk about our use case today. Our use case, we are going to be discussing about carbon output. So we have OECD. Now, what is OECD? It's an economical development body. So basically, it's the full form is Organization for Economic Cooperation and Development. So we have a lot of countries coming together trying to build an organization where we are going to be where they are trying to develop some sort of global organization planning. All right. So what is going on? This has 38 member countries, and these countries collaborate when it comes to their economic and trade policy. All right. So we are trying to see how are these countries performing when it comes to emissions. Now, emissions are a very, very important point. Emissions are going to be very important when we talk about the future, how the future is going to look. Carbon emissions are going to have a big impact on the overall global environment. So we are trying to put in place regulations to limit the carbon emission from different countries. Right, we are trying to put a limit on these CO2 outputs. We are also, putting in place a lot of regulations. We are putting in place a lot of fines, etc. So we are trying to measure here whether the countries are actually following this overall emission responsibility or not. Now, this overall emission responsibility varies country by country. So different countries will have different level of overall responsibility. All right. So we have something called as the Paris Agreement. So Paris Agreement was an agreement that was signed in 2015. This was an environmental agreement that was ratified by all countries in the world. The aim of this agreement was to put a limit to overall carbon emissions in the world. For every country, that is what the aim is. Okay, we are trying to put a limit on how much carbon emission we are producing. All right, obviously not all organizations, few countries did not join, right? We are facing a situation where a 2-degree overall temperature increase is going to have catastrophic impact on our overall living conditions. All right. So within this, we are trying to put a limit on how much carbon each country is emitting. So our goal is to make sure that the overall temperature does not rise by 2 degrees. Also, the goal is to have a carbon neutral world by 2050. So we are trying to push for renewable energies. So let's take a look at our data set and try to understand what is going on here. So this is our data set. We are talking about metric ton of carbon emitted by different countries in the world. Let me open the CSV file that I have and will use the CSV file. Just a second, please. All right. So this is our CSV file. So what do we have here? We have the overall emissions. All right. So this is the first row is depicting the overall emission, and then we have a country-wise breakdown. Now this data set was collected from OECD organization. So they have given individual values for these countries. So we can go through them. We can see like we have countries like Australia, Austria, Belgium, right? These are all member nations. So we have 38 members. All right. Then we are also looking at a few of the non-member countries here. Like we have India as well here. So we are trying to see whether these countries are following within the overall carbon emissions or not. Okay, we are trying to figure out whether they are following this limit or not. Now we have to remember that countries like India and China, they are non-members. All right, we have not joined this organization. Okay, we are not also under review. We are not even trying to negotiate joining this organization because, excuse me. because the overall aim of this organization is to put limit on how much carbon emission can be put across. Now look at a country here. Look at United States and then compare the carbon emissions for United States versus China. Obviously, China has higher, but Chinese population is also 4 times higher. Okay. So China is producing a lot of carbon. There is no denying that. It is having a negative impact on our environment. There is no denying that as well. But in terms of overall emissions, is it really as bad as United States with its less population and higher carbon emission per capita? Anyways, that is a different conversation for a different day. So this is our data set. So we are trying to predict the future carbon output. All right. So let's look at the data set. And now we'll take a look at the data types. Now here we can see that the data types are all objects. So first what we'll do is we'll drop this unnamed one column. This column we don't need, so we'll drop it. So now if we look at our data set, we have this. Now the next thing we have to do is we have to convert each of these values into int values. So what I'll do here is I will create a new data frame that will be a copy of the other one. So we have this data frame 1. So then what we'll do here is from data frame 1, we will drop the location column because that column can stay as an object. All right. Then we'll convert it to numeric. So what is getting asked here? Okay. All right. Just give me a second. So first thing I guess we have to do is we have to replace the comma. So what we'll do here is we'll do df1 dot replace, and we'll replace our comma with empty space. So if we look at our data frame now, has it not removed? Okay. So just give me a second here. Let me check what we can do. All right, I'm just trying a line of code. Hopefully that will work. All right, so here now we have removed those columns, those commas. So let me quickly restart the kernel, and then we'll continue forward. So we'll check this. So removing the commas has automatically removed the requirement for having the requirement for needing to change the data frame type. So what we'll do here is now we'll do some analysis. All right. So first, as always, we'll check for any missing values. Do we have any missing values? We do not. Then we'll use the describe function to take a look at our overall data. So as you can see that what information can we draw from here? The mean overall emissions has been constantly rising. Okay, the maximum value, the minimum value, all of them have been steadily rising. Although it appears that around 2030, it slowed down. Okay, so what we'll try to do here is let's try to plot. Let's take a data frame, the original data frame. So here we'll drop the location column. Again, I forgot to mention the axis. If we don't mention the axis, the drop function doesn't work. So here we go. So what we'll do is we'll draw a figure of some size. We'll just draw an empty figure. And in that, we'll try to draw a line plot for all the years. Okay. We'll try to draw a line plot for all these years. So we'll ignore 1 second. So I guess we have to use plt.show. Let's try this. Still not showing. So maybe we cannot use this. Okay. So here we see the year by year outcome for each of these columns. Okay. For the second, let's check something quickly. So here we have the histogram. So this loop is not working for SNS Seaborn. So we'll try to plot some other values. So we can take a look at 2005. Okay, it is not able to plot for any of these values. Maybe it is not able to read the data. So let me try some other way. So here we have the line plot for all these values. Similarly, we can also take a look at the pair plot for these numerical columns, because we will be using only the numerical columns going forward. This pair plot will give us an idea on the relationship between the overall emissions year by year. Are they in a linear relationship? If they are in a linear relationship, what sort of linear relationship are they in? And based off of this, we can say that the relationship looks quite linear. All right. So then we can create a correlation matrix where we'll try to judge for that. So as you can see, they are almost all perfectly linear to each other. So this can create a problem of collinearity as well. So we'll try to solve that collinearity problem. First, we'll try to solve that collinearity problem and we'll try to see how it can affect our model. So first we'll use standard scaling to reduce the range of a number. So our data, our entire data, we will use the standard scaler on. We'll not be using it for specific columns because here we are dealing with entirely numerical data. All right. So the next thing we need to do is we need to redefine the column names. All right, we need to first convert it into a data frame, and then we need to redefine the column names. So df1 columns equal to 2005, 2006, 2007, 2008, 2009, 2010, 2011, 12, 13, 14, and 15. So these are our column names. Right. So now if we look at our data, here we have our data. We can also do the describe call here. We can look, the mean is near 0. Standard deviation is nearly 1. All right. So now we'll try to build a regression model. For regression model, we'll use stats model. So we'll build our first model using ordinary least squares. So here we are trying to see if we can predict the current year data using the previous year data starting from 2005 all the way to 2014. So we can also take some specific years here. We don't necessarily have to go all the way back, but for the first model, we'll start off using this. And then we'll try to refine our model more and more as we keep going. All right, so we have up until 2014, and then we have to define our data, which is df1, and we'll say dot fit. What happened here? Number besides 0 and 1 only allowed with. So here what I'll do is I'll rename the columns into some numerical values that we can understand. In order to avoid a situation like this. Right? What happened here? I think we need to rerun this line first. All right. Then let me quickly check if this is working. Yes. All right. Now hopefully this will work. All right. Perfect. So now we just need to replace these values. So now that our model is built, we'll check for its summary. Can we predict the 2016 outcome using this? Our R squared value is 1. We have to check for this p value. P value is greater than 0.5 for a lot of these columns. That means we have a problem of high collinearity. Okay, so we'll try to check for this high collinearity problem. Okay, so what we have to do here is we have to build variance influence plot for each of these columns. So starting off, first what we'll do here is we'll try to check if this issue still exists if we take less number of columns. Let's say we are taking from 10, 11, 12, 13 and 14. Only if we are taking these columns. All right, not by taking all the columns. We'll still use the same data frame, the normalized data frame. And we'll check for its summary. So we are still having the same problem. Here, we can see that the p value only for 13 is very high. The rest of them are low, but we still have to verify that issue. So what we'll do is we'll check for all the models starting with 10. We'll check their relation to each other, not to all the columns. We'll check for 11, 12, 13, and 14. We'll take the data as df1.fit and we'll try to check for its variance influence factor. So like this, we have to do for 11, 12, 13, and 14 as well. So I'll just quickly do that. Instead of writing this repetitive line of code again, I'll just quickly replace all these values here. This will save us some time because we might not have sufficient time to do all of this. We'll check for 12 next. Then we'll check for 13. Then finally, we'll also check for 14. What we are trying to see here is whether any of these columns are specifically having a bigger impact than they should. What is their variance influence factor? So whichever column has the highest variance influence factor, they are causing a problem of multicollinearity. Oh, okay. Here we don't have to use, we have to use R squared. My apologies for this. Here we are trying to check their R squared values. Making too many mistakes today. And most of these mistakes are avoidable. All right, finally, we get it done. So then I'll create a new data frame. I'll call this variables we have here. What are the variables? We have 10, 11, 12, 13, and then we have 14. And then we are also looking at the variance influence factor. And that is our VIF 10, VIF 11, VIF 12, VIF 13, and VIF 14. Then we'll convert it into a data frame using pandas. and then we'll take a look at our data frame. So as you can see, the highest variance influence factor is caused by 13. Okay, so what we'll do is now we'll split our data and we'll build our model without using year 13. Okay, so we'll use the train test split. So we'll have training data and we'll have some testing data. We'll be using the data frame where we have normalized the function. So here we will take the training size as 30% because we have a little smaller data. So I want sufficient amount of data to do the testing. So we'll build our final model using ordinary least square. And we are trying to predict 15 using 10 plus 11 plus 12 plus 14. Our data is df1.fit. So then we can also look at its summary. So as you can see that the p-values are not greater than 0.05. So we have fixed the collinearity problem. Then what we'll do is we'll try to predict the test results. So we'll predict the test results using this final model. All right. And then we'll check for the residual here using the predicted value minus the actual value. All right. And then we'll quickly do its RMSE to see how close to the actual result was our model. So we are just building. So here you can see how we have built our RMSE function. Quite simple. And our RMSE function gives us 0.005%. So that means we have built our model that is quite close to the actual value. We are not facing much issues. So this is how we can build a linear regression model. So with this, we come to an end for today's session. So thank you everyone for joining.